So this video is on the impulse momentum theorem, which is chapter 11-2 in the textbook. Okay, so first, the main topic of this chapter is going to be collisions. Now, in general, collisions are complicated because if you have two objects that are colliding together, in general, the force between, so there's going to be a force on object 1 due to object 2, a force on object 2 due to object 1, and in general, that force is going to change with time as the collision happens, and typically that's a complicated thing. But we're going to use this idea of impulse and momentum to actually make things a little bit simpler. So if you imagine, in a small time interval. So if you start with Newton's second law in terms of momentum, remember the net force on an object is equal to the time derivative of the momentum. Now if you split apart those differentials, you can say some little change in momentum, dp, is equal to the force times some small time interval dt. So if you then imagine taking the integral of both sides of this equation, so you integrate dp, well, the integral of dp from the start of the collision to the end of the collision is just the change in momentum, so p final minus p initial. And then on the right hand side we've got the integral from t1 to t2, so that's when the collision starts to when the collision finishes, f dt. So the right-hand side of this equation is what we're going to call impulse. So your textbook likes to use a capital I for impulse. Sometimes it's also written as a J, but it is a vector, so it's a vector quantity, and it's defined as the integral of the force over the time interval. And this leads to the impulse momentum theorem that says, well, the other side of that equation was just the change in momentum. So in other words, what this means is that if you look at the total impulse on an object, right, so if you've got multiple forces, you just take the sum, the vector sum of all the impulse from each individual force. So the total impulse has to equal the change in momentum. So that's the impulse momentum theorem. Now, one other thing we can do, so in general, the force during this collision is going to be a complicated thing. So that's what this plot on the right is supposed to represent, right? So you've got some Ti, which is when the two objects initially start to come into contact, and Tf is, right, that's the end of the collision. So you've got a force, some non-zero force between T initial and T final, and in general, as they start to come into contact, it's going to get bigger, and then as they start to go out of contact, it's going to get smaller. But what we can do is we can actually use this idea of impulse to define an average force. So if you think about what impulse is, well, it's the integral of force over the time interval dt. So really it's the area under this magenta curve. So what we can do is we can actually define an equivalent area. So that's this little greenish colored box. So the area there is supposed to be the same as the area under that magenta curve. And you use that to define this average force. So the average force is the force that gives you just the right area to where it's over the time interval, it gives you the same impulse. So we can also think of this change in momentum as the average force during the collision times the macroscopic time interval delta t. So, and just a note here, and in this example, and in basically every example we're going to do in this chapter, we're using something called the impulse approximation, which says that the force between the objects in a collision is the dominant one, and any other forces that may be there, gravity, friction, air resistance, whatever, all those are negligible. And typically this works as long as you kind of restrict yourself to right before the collision and right after the collision. And if the collision time is short, then this is going to be a pretty good approximation.